Hey, what's up everyone? Jason Turley here, and I've been getting more into Linux kernel security, and a great resource that I've recommended before for learning about these low-level things and these more computer science and computer security related topics is a website called Pwn College. It's set up and run by some professors from Arizona State University. And they actually have several lectures and modules where you can go through and watch actual lecture videos or click through the slides. Usually they have additional resources and further reading. And then like my favorite component of this website is that they actually have like CTF challenges that you can go and solve, and you can actually apply this knowledge. You can get hands-on skills with the material that you have learned from the lectures. So this is all about the Linux kernel and different security mitigations and exploit techniques. And if you're familiar with userland exploitation and bypassing ASLR and data execution prevention and NX and using ROP gadgets and things like that, those things do exist in the kernel as well. They are a little bit different. The shellcode that you write for the kernel is going to be different than shellcode you write for a user space application. And that's typically because for a user space application, you are utilizing syscalls, usually something like execve or find some way to run bin.sh using a system call. A system call is something that a user space application or program will use to interface with the kernel. When you're exploiting a kernel module that we'll see later, you're not really going to be using syscalls because you're already in the kernel. You don't need that API. It'll be a little bit different, but those are for later videos. In today's video, I want to start simple. If we click here and expand this level 1, we see it says ease into kernel exploitation with this simple Crackme level. And you can even start it up and it will give you your own virtual environment. You don't need to install anything. And that's something I love about Pwn College. They set up the infrastructure and environment for you, so you can really just focus and hone on and learn about whatever topic it is. You don't need to worry about, do I have the right computer for this? As long as you have an internet connection and you log into this website, you can have your own dedicated environment where you can do different types of cybersecurity CTF challenges. However, this is part of ASU, Arizona State University. It's part of their curriculum, so I don't want to showcase any challenges because students might be able to use that for cheating and things like that. So instead, the next best thing I could think of is actually creating my own Linux kernel module, Crackme. So I have my Kali Linux VM over here. You can do this on any virtual machine, any Linux VM. Essentially, there's a few things you need to install, but as long as you can program in C, which the majority of kernel modules and device drivers are written in, you should be good to go. So I made a very simple Crackme here. We can actually see the source code right here, crackme1.c. Let me just do a file star, and we can see the different things I have in this folder. We have the C source code file. Maybe we'll get into that later, but what I really want to focus on is this .ko. KO is the extension for a kernel module, I guess kernel object here. And this is the actual device driver or module that will get loaded into the kernel. If you want to see what is currently loaded in your kernel, you can just do an ls mod or list modules, and it'll go through and it prints out the different modules loaded into your kernel. There will be some that are automatically installed. It depends on your distribution and what other software you might have. So that's kind of neat. So we made our own kernel module. Right now we want to insert it. We want to shove it inside of the Linux kernel, and that's the beauty of it. So I didn't really explain what a kernel module is. All a kernel module is, it's a way to kind of dynamically inject or load code into your operating system or to your kernel. You can dynamically add and remove them. And once we start reverse engineering this, we will see some of the different functions that you can implement. So once again, kernel modules have this .ko extension. In order to shove them or insert them into your kernel, you need to be the root user. So we're going to say sudo or super user do insert this module, crackme1.ko, into the kernel. So we hit enter. It's going to ask us for our password. and then it's not going to return anything. Usually a return code of 0 or nothing indicates success. Now, this is a kernel module I created, so I know it has some useful logging information when it's inserted and when it's removed. If you want to look at the kernel messages on your system, there's a few ways we can do it. I'm a fan of just doing dmessage and piping that into tail because the output will be pretty verbose. So if we see here down at the bottom, we see the name of our module, Crackme1, and then we can see this is actually kind of a warning saying, hey, loading this out of tree module taints your kernel. Module verification failed. I haven't looked into this too much. I believe it's just because this is a custom kernel that kernel module I created. I didn't necessarily make sure it is the most up-to-date or secure or follows whatever best standards or security practices. So I am getting this warning, but we see that it is inserted just fine because down here I do see my logging messages being displayed on the screen. It's saying, hello, this is a kernel module Crackme challenge. Enter the correct password to win. And then it actually tells us the name of the file it creates in /proc Crackme1 /proc is a virtual file system. So if I do an ls tech l on /proc and let's just say CPU info, we see it returns a size of 0, right? So does that mean it's an empty file? Let's see. So if we actually try to cat this out, it does display information. So the proc file system, these are essentially kernel modules they're almost like sleeping, right? They don't do anything until you interact with them, whether that's sending data to it with a like echo please sub, and then redirecting that to the kernel module. So that's one way to interact with it, doing a write, or you can read from it like we just did with cat. So that's why they take up 0 bytes when you look at it with ls. I don't want to say it's not there or that it's not taking up any space. I don't think that's factually correct. However, they are empty until you interact with them. Kind of a weird, kind of a cool trivia thing. So this is our kernel module that we created. We can verify that it is loaded with doing a ls mod and then grepping for our kernel module. It puts an underscore here instead of the hyphen that we had for whatever reason, but we do know our kernel module is loaded and it did create an entry in proc. So let's see what happens if we just try catting this out. It says, hey, enter the correct password in order to win. So let's just do please sub, like, is this the correct password? And slam that into here. Cat, it's like, no, please enter the correct password to win. If we wanted, we could do dmessage tail. Does anything else come up? No. So we know we need to analyze this kernel module. Hey, I know I already have the source code here. Maybe we'll look at that at the end. But if this was like a real CTF challenge, you probably wouldn't be given the source code. You would just have the kernel module, and this is just an elf file, right? So if I do star.ko, this is just an elf file, and we do know how to analyze these in a disassembler or a decompiler. I'll be using Ghidra, which you can install that now with sudo, yes, I agree, sudo apt, come on now, sudo apt install Ghidra, and that's one way you can download it and install it. It makes it a little bit more useful. So here we are, we have the menu for Ghidra. It's saying, hey, no active project. So let's go to file. Oops, click the wrong thing. File, new project. This is a non-shared project. It's just for me. I'm not sharing it with any coworkers. I'm not collaborating with anyone. Let's click on next. Let's store that actually in our directory that has our kernel module. And we'll just call this Crackme Ghidra. Hit finish. And now we have our little tool chest. We're going to click this dragon icon here to open up the code browser. Right now, I'm going to go to File and then Import, or you can just hit Control I on the keyboard and we need to import our kernel module. You see I have a few here. Let's go to CTF and then click on this one. It recognizes that it's a 64-bit ELF file. It was compiled with the GNU C compiler. Sounds good to me. It's going to do some processing, and then it's going to actually ask if we want to analyze the file. I don't see a reason why we shouldn't, so let's click yes. I just leave the defaults. This is a very simple challenge, so let's leave that there. Okay, hopefully this is large enough to see without it being too distorted. For whatever reason, these PFX prefixes are added here, but we see these are essentially the functions that we have access to. And if we didn't want to look at it here in the disassembly view, if I come over here in the symbol tree and I start clicking around on functions, we can see some of the modules, or some of the rather utilities and the functions that are added here. So we see a Crackme exit function, Crackme init, one for reading, and one for writing. So every single kernel module that you create that you want to load in the system will have an init function, and it'll usually follow the same formula, the syntax of whatever module name you want, and then underscore init, and then same for exit. As the names kind of imply, the initialization function, that's all the code that you want to be run when you do that sudo insert mod and then your kernel module. So when we did our sudo insert mod crackme1, it did call an initialization function that printed out the contents of this right here. And then when we do a sudo remove mod on crackme1, and I can tab complete that, it will call the exit function, and we can see if that printed anything as well. And we see here it did. We see the timestamp is proc crackme1 has been removed. So if I try to ls that file saying, hey, no such file or directory. So let's go ahead and reinsert this. Control R to search sudo insert mod. There we go. And let's just do another ls mod. So it's there. So those two functions will be included in a kernel module that you create. If it's something that is already statically compiled or built or shipped with your kernel, it might not have that module exit command because you wouldn't necessarily remove those modules. So to save space, those modules that are there by default, statically compiled into your kernel, might not have an exit function. So we can come over here inside of the decompiler now, and we can look at the code for the exit function, or the crackme init function. Now Ghidra doesn't always give it the best variable names. It kind of just gives it, hey, these registers are 8 and are 9, but we can kind of look at the different variables and some of the functions that it's calling. We see something called proc dir entry, so proc create crackme1. So this looks very similar to this file that was created in proc, right? Proc crackme1 looks exactly the same as this. So it's creating an entry inside of proc. It's giving it some flags. It's setting something called proc file fops. Let's see, can I double click on this? Would it actually define or tell us what this is, what this symbol is? Find, search all. No, it's only defined here. So I guess to spoil it, later we'll look at the C source code, but however, file operations, this is telling the kernel module what to do when certain actions take place. It's a huge structure, and the ones we have implemented here, and you can see them in the functions folder here, is read and write. There's more for open and release. So anything you can do with a file, any operation you can take on a file, if you want, you can explicitly define those inside of your kernel module. So I implemented ones for reading and for writing. So we see here on line 16, we're checking if the proc underscore file that we created is null. So if there's an error, right? So usually functions in C that return a pointer will return the null macro, or the null, I guess, hard-coded variable, whatever you want to call it, on failure. So if we failed to create a entry in proc, It'll print a message to the screen, and then it returns negative hex C, which I think is 12. We can convert that to decimal. It will return negative 12. And if we succeed, it will print out those messages that we saw earlier. Is there a way to resolve what these strings are? Probably, but so we know it'll, so this init function, essentially all it's doing is creating a entry inside proc. If it succeeds, it prints out these messages. And if it fails, it'll return negative 12. On success, it returns 0. So let's look at the exit function. Hey, this is very simple. All we're doing is proc remove. We're deleting that file that we created earlier, and then we're printing a little message, an informational message to the screen. So what we're really interested in is the read and the write. The read function is called whenever you try to read from the file. So like what we did with cat, when we did a cat of proc CPU info, it printed out all the contents and info about the computer processors on our device. So when we did the same thing for this, it's printed out a message saying, hey, enter the correct flag to win. So let's actually look at this function, crackme underscore read. We see it returns a signed integer, and it takes 1, 2, 3, 4 arguments, a file pointer, some type of buffer, the length of that buffer, and then an offset. We can see some of the variables being defined up here. We see an authorized flag. So if authorized is true, it'll print out U1. Please like and subscribe. However, so if authorized is false, this is the message that we saw earlier, enter the correct password to win. So how can we set this authorized flag to true? How can we get this case to work? And then we can see some other system calls here. Copy to user is taking something, a string or a message from kernel space and supplying that to user space. So in our case, standard out, and then it updates the offset of basically how much data we have read from this file. So nothing too crazy here. Let's go to the write function now. So this is the function that will actually check our user input and compare it with whatever flag. So kind of just scrolling down and perusing through, we see a destination buffer of 64 bytes, another buffer of 8 bytes in size. This GS register, this offset thing, if you scroll down, you also see a stack check failed. So essentially what this is doing is checking for a canary. A canary is a special value placed before the return address by the compiler. It's usually randomly generated. It changes every single time the program runs typically. And so if you do a buffer overflow, you overwrite the canary as well as the return address. So the compiler will check the output of its expected canary and then what you overwrote it with. And it's a way to tell if you are doing something malicious, like a buffer overflow. There are ways to get around canaries, but that's outside the scope of this video. Trying to stay on topic here. Let's just focus on the actual core of this function. We see a length check here. So this is good. This is doing some type of bounds check. We take the length from the user. We're saying, hey, what is this? Is this 64? Yeah. So if length, so essentially we're doing some check. We're making sure the user, whatever input they supplied, let's say they supplied something that's like 100 bytes long. That won't fit in this destination buffer. So we're kind of just truncating and making sure that length is actually set to the correct value, and we don't have any type of buffer overflow here. And now we see a for loop going on for some reason. If we come down here, now we see a function called copy from user. Before we saw copy to user, that's taking something from kernel space and throwing it over in userland space. So this one does the opposite. It takes a buffer from user space and assigns it to a buffer in kernel space. So this is a pretty important function, and this is why you always want to make sure when you're doing kernel module programming that you have really good length checking and bounds checking, because what if we didn't? What if we didn't have this check up here and we didn't ensure that the user's input fits in our fixed size buffer, right? Because if you get a buffer overflow, in a user space process, and you can get let's say you get a buffer overflow and you execute shellcode. Your shellcode runs as whatever privileges that process is running as. So let's say you're exploiting a web service that runs as the www data user. If you do a buffer overflow exploit, when you get your shell, you'll be running as that www data user who might have limited privileges or permissions. However, here in kernel space, if you can get a buffer overflow, you can make sure you run as that root user or that admin user, that God user who has more control of the system and whatnot. So buffer overflows here are a big deal. We do see a stack canary being set. So even if we did want to do a buffer overflow, we need to mitigate that canary somehow. But right here, we can see our favorite function, stir compare. So it's comparing what looks to be user input. So this is a terribly named variable, stack underscore 70. We see it here as the first argument for copy from user. We can rename this if we want. We can just call this user buffer. And if we weren't sure, we can always look at the man pages or lookup or Google copy from user and see the arguments that it expects. So it's comparing our user supplied input with this value. And if they are equal, authorize will be set to true. And then when we go back to our read function, we see if authorize is true, it prints out you win. So if we come back to the write function, we can see what the password is here. So we didn't actually need to reverse engineer and look through this code. We probably could have just looked at the strings. How do I do that in Ghidra? I haven't used it in a while. I've more so been focusing on trying to learn IDA Pro. Let's go to search for strings, minimum length 5, search all. This looks good, hit search. See if we can make this bigger. So yeah, we can see the strings this way. My preferred way of looking at strings is honestly just looking at the command line. So if I do strings on our kernel module, let's pipe this into less because it'll have a lot of output. We can start seeing some of the ASCII output, right? Copy from user failed. Hello, this is a kernel module, Crackme challenge, enter the correct password to win. And then right underneath that, we see this value. When I was goofing around and playing with this, I believe I just did echo LOL and pipe that into MD5 sum. And that's how I got the correct hash, or that's how I was able to figure out what password to use. So our kernel module, let's make sure it's still there. So let's do a cat one more time, enter the correct password to win. Let's do an echo of this password into proc Crackme1. Let's cat this out again, saying enter the correct password to win. I have to do attack N. There we go. Attack N tells Echo not to write that new line character. A new line is a 0A in hex. So do not add that. Just write the string exactly as you see it here. And we see that we won. And we can look at the D message output if we want. There's no fun like win message here. You can also just do journal CTL, tac sense, let's just say 10 minutes ago. Maybe that wasn't long enough. Let's say 40 minutes ago. And we can see our messages here. So I like doing dmessage tail, but you can also look at journal CTL if you want. So that's really it for that challenge. If we really want, we can look at this crackme1.c source code file behind the scenes, extra credit. This is the actual code that I gave to a compiler and told it to generate that kernel module for us. So just looking through, we can see some of the inclusion libraries we have here. So if you're familiar with programming in C, some of the standard libraries you'll use are stdlib, stdio. You're not going to have access to those here because those are standard C library utilities, and we're in the kernel. We're underneath that essentially. We don't have access to those userland libraries or system calls, so we have to use these special header files included in this Linux repository or folder, right? So kernel.h, module.h. There is a string.h, which is helpful, and that's how we're able to do a string comparison and things like that. But they're not always the same as the ones you see in the standard C library. I was being fancy and I added this kernel version header check because older versions of the kernel before 5.6, you could use the file operation structure that I have highlighted right here. However, on more recent versions of the kernel, if you want to create something in /proc, you should be using the proc ops structure. They're essentially the same. We can actually look here and we can see the functions that we want for when we read from the proc file and we write to it. So when the proc file is read from, we will call Crackme read, and we see the definition of that here. And when the file is written to, we call Crackme write. So more modern versions of the Linux kernel, you might see these proc ops structure. However, when I was first learning about kernel module programming in university a few years ago, we did learn about file operations structure. So you will see this a lot. You will see underscore operations, whether that's for files or process, proc directory, or inodes. So it's not too difficult, I think, to understand what it is and what it's doing. And we can scroll down here and we see the init function. Hey, we're just creating a process. I gave it this macro of challenge name. If I put my cursor over it in Vim and I hit Shift-3 or the pound key, I can just kind of navigate automatically to everywhere macro or this variable is defined. So our challenge name is Crackme1. So we're creating that in the process directory. We're setting permission 666. So it is readable and writable, I believe, but not executable. Just read, write. I forget what null is here. And then we're giving it that process file operation structure that we defined up here. If that fails, it'll print an error message and return a negative value. And then if it succeeds, it prints these messages that we saw earlier. And we have the Crackme read function that's called when the file is actually read from with something like cat. So this is very, very similar to the decompiled code that we saw in Ghidra. We see no function is too long. Nothing has like 100 lines of code. So I do kind of like that about these kernel modules. It's easy to kind of break it down. Like, hey, I only want to focus on this write function right now. There's not too much that's going on. These are just variables being defined. We're doing a length check. So if the user enters something that is more than 64 bytes, we truncate that to the length of 63. Buff max lane, that's a macro defined. So this is 64 minus 1, so 63. And we're copying that many bytes from the user. And then we're comparing it with the actual hard-coded password. And then we have this Crackme exit function. All it's doing is removing an entry from the proc /proc folder. And then we can see here, we have module init and exit. This is what's telling the kernel module to actually use these functions for module init and for module exit. And then we just have some simple license information here, a description, and who the author is. So that's really it for this video. Let me just remove this module, sudo remove mod Crackme1. Hopefully this was useful and helpful. I was kind of going slow and trying my best to kind of explain what's going on, because if you've never worked with kernel modules before, they can be a little bit confusing. However, they're nothing I think you should be too scared about, too worried about. If you do want to learn more, I highly recommend going through Pwn College. You see I've solved a little under half of the challenges here, and we scroll through and kind of look at some of these later ones. We do see it is asking us to write shellcode and do privilege escalation. So once again, I can't highlight and showcase the actual challenges from here because it's college material, but I can create my own. Crackmes or vulnerable kernel modules as a way to showcase these different cybersecurity concepts. And I think I'll do that if you guys enjoy this, if you like learning about the Linux kernel and at least the modules that you can insert yourself and reverse engineer if you need to. A lot of kernel modules are open source, thankfully. You can find those online and just look at the C source code, or you can download them locally and poke through them in like a text editor. However, I kind of want to get better at reverse engineering, so I just wanted to load the finalized product, the finalized kernel module, and just look at it in something like Pro or Ghidra. So hopefully this was cool. Hopefully this was interesting. It's a little bit different. I will crank through and knock out some more of these challenges. And as I learn, I'll showcase that on the channel. And yeah, that's really it. Hopefully you guys enjoyed this video. Like, comment, and subscribe. And as always, guys, take it easy, and I will see you in the next video.